Good. For the next one, oh, sorry, wrong button. For the next one here, same idea, right? In this case, the initial value is 300. The growth factor, right? Well, it's growth in this case because your B here, 1.09. That's greater than 1, right? Greater than 1. And here, our rate, right? How would you get the R in other words? Well, your B here, your base is 1.09, bigger than 1. So we have 1.09 minus 1, again, using this, right? And that's just 0.09. And that's what we get. And then for the next one below it, this one's a little bit different, right? I mean, the initial value is, of course, different. You know, the initial value, of course, is, let me just see something. Okay, the initial value, of course, is different. We had 3,900. It's decay now, though, right? Because what you're raising to the x, your b, that's less than 1, 0.95. So what would r be? That's going to be 1 minus this, which is 0.05. These two are kind of obvious. It's written in that form. So, and here also the last one, you know, again, we saw this last time. The initial value is 400, 0.55 to the x. You're raising, so your b here is 0.55 decay because it's less than 1. And we get this, 0.55. B is 0.55. So how do you get r? You get 1 minus that, like so. Okay. You should be reading the book as well. There's definitely more examples there. Are there any questions about this? Okay. Well, now what we're going to do is see an example where exponential decay comes up. And it does come up, for instance, when you have what's called radioactive decay. And in particular, this leads to the concept of half-life. So let's suppose, so again, this is just a word problem I made up. Suppose we discovered a new substance. I don't know what to call it. We're going to call it element capital X. Okay? Now it turns out I'm not sure how it works and, you know, the chemistry behind it or whatever, but it radioactively decays by 21% each day. And here I'm just saying what that means. That means, you know, after a day goes by, the amount you have, 21% of that is gone. It breaks down radioactively. You know, so whatever amount you have, when the day ends, 21% of it will be gone. Okay, so let's suppose, for instance, we have 200 milligrams of this. Let's find out how much will remain after a week. Okay, notice though we have exponential decay, right? Because the amount of this substance is changing by a percent, right? A constant percent. We're saying it's decreasing by 21% each day. You know, if we said something like it was decreasing by 21 milligrams a day, then it would be linear. Okay, so we have exponential decay. So we know, since it's decreasing at a constant percent, we know it's exponential decay. Not only that, we're given the percent, so R we actually know, right? The decay rate is 21%. So our R is 0.21. So our R is 0.21. And of course, it's given that the initial amount is 200 milligrams. So we're going to write the amount as a function. Again, this is our exponential decay. I'm calling the function f. We get this. 200 times 1 minus 0.21 to the x, which of course is just this. So that's what we get here. All right. All right, so that's good. So this is our function. Does it make other questions about how I got this? Okay. Okay, so that's our function, right? That's, it's exponential decay. We found our R. That's just basically the percent, the decay rate written as a decimal. And we get this. Okay, so that's good. So how much of this will be left after a week? Well, we know a week is 7 days, right? Remember, where is it? It breaks down each day. So our unit of time would be days. So here, f of 7, right? A week is 7 days. That's this amount raised to the 7, which turns out to be this when you round it to 2 decimal places. This is something you could definitely do in the calculator. So, we're not graphing this, but again, computers, iPhones and stuff, they all have calculators built into them that can do this. Now in 2, it's the same problem essentially, but now we want to know how much is left after 14 days. Not 14 additional days, 14 days, right? So the amount left over then would be this. After 14 days, right? We're raising it to the 14. That turns out to be this. How much will be left though after 30 days, roughly a month? Well, that's just a function at 30. That's what this is. That's what 30 is. That's f of 30. So again, how much will be left over after 30 days? So again, that's the function evaluated at 30, which is this. And that turns out to be 0.17. It actually turns out, I know the numbers here are getting smaller, and they're positive, of course. It actually turns out this will never, ever get to 0, no matter how big your exponent is. In other words, this is our f of x here, right? No matter how big this x is over here, you're never going to get, you can never find an x so that this whole product equals 0. So in theory, the substance will always going to have some of it. We're always going to have some of element x. It's never going to completely vanish. All right. Okay, so the next one I just want everyone to try. Basically, you're just going to get the formula, and you're going to determine how much is left after a week. It's very similar, except the amount and your decay rate are different. So let me just pause the recording, and I'll give everyone about 5 minutes.